morning, everyone. Back at you from Cornell University on a computer using an operating system that is apparently supported by you, namely Windows. And hopefully you can all see here the software system design webinar, as was so hyped. And if you are still here, then I applaud your bravery for persisting through technical difficulties. It's a good thing I'm leaving the presentation about how to design a software system for a submarine, not to how to run Google Hangouts, because apparently I don't know how to do that. So, software system design. The goal, of course, of RoboSub is to win, to build a vehicle platform submarine that can complete the competition successfully and accumulate the maximum amount of points possible. To do that, we have to consider a few things: the environment, the pool, TransDeck, various tasks, Dave's rule set. Tasks define a set of things that can be done, the goals, if you will, a set of points they're rewarded with, and the rule set defines a set of restrictions and parameters for how you can accomplish these tasks. And you have the submarine, which has sensors, cameras, acoustic, otherwise ways in which you can perceive the world around you, and actuators, thrusters, manipulators, whatever sort of ways your robot can change tasks can affect the state of the world in order to accumulate points. And then, of course, is the vehicular platform itself. And from that, you have to do some magic in order to allow your submarine to make the optimal decision given known information, given what you know about the world and constraints, which you know you can do. That magic is an ideal software system. That's what software is supposed to do: allow the submarine to transform a set of inputs into a set of outputs, a decision heuristic. Now what? Software consists of a few things. Most people think of software as programming. Programming can be algorithms, how you might maneuver around the pipe. A lot of it, especially when we test, is correctness and bug testing. You know, which buoy do you want to be hitting? Are you doing it correctly? If not, why? Figure out what the problem is. And of course, tuning and refinement in somewhat of a similar vein. Changing vision parameters so you can pick up on the torpedo target, even if it's green against a green background. Making sure you don't see the sun by accident and recognize it not as an object, etc. That's not software system design. Software system design is sort of like a meta programming. It's the ideation and development that leads ideally to an effective software structure. What you need to do in order to create the kind of high-level structure that will enable you to program a submarine effectively. Which sounds kind of vague, I'm sure, but fundamentally, software system design sort of consists of a few parts. At a very high level, simply a matter of segmentation. Yes, at one level, you have one piece of software, and that piece of software runs the submarine. But you want to be able to split that piece of software into individual parts that are ideally as independent as possible, that act on their own, have some strictly defined function that they perform, say a vision system or a mission system or simply a piece of code that takes an average of two numbers. You want everything to be segmented such that you can test things individually. And of course, when you have multiple parts, you need a way for them to communicate. You need to enable data transfer between the system that's taking in vision data from cameras and transforming it into object coordinates, for example. Essentially, software system design is the process of writing code that will allow you to write code, writing the high-level structural framework for a system that will allow you to focus in on the individual programming that you're doing, say, to ram them. Oh, I should mention, if anyone has questions during this presentation, my email is cwg46@cornell.edu. So you can see there on the slide. Feel free to send anything my way and or just put it in chat on Hangouts, and I will address it as asked or at the end. Back to system design. In some ways, as I alluded to earlier, you can consider software system design as a kind of meta program, which sounds like something an MBA might say, but it means something. In a way, you're sort of maximizing the effectiveness of your programming. At a very basic level, a sub is simply one program, but when you have one interdependent program that's not really segmented into parts, maybe it's just a 100,000 lines of code that you go through and execute one by one, that runs your submarine. But when you have that kind of architecture, it's very, very hard to test and change things. And for those of you who are, as many are, doing CS in college or have worked on large CS projects, you know that a lot of the difficulty in working on large projects doesn't really have to do with the correctness of the code itself. It just has to do with the design of the project and understanding all the various factors that affect your code, understanding all the other pieces of code that will use your code when you write code. And so the way to deal with that at a very high level, the way to engineer an architecture such that you really can have all these complicated pieces of functionality that need to interface with each other and do so correctly, is, at least to the degree to which you can, splitting everything into independent subsystems, splitting your massive software stack, which has to perform the mammoth task of taking in some information about the world, about the pool, sensor data from your camera, and outputting information about what you want the submarine to do. And you want to split that up into independent subsystems, each of which has some specific defined purpose, which you can develop individually on the programming level and test individually. If you have a filtering module, for example, you don't need to worry about how it interfaces with the vision system or your measuring system. You just need to provide a sample set of inputs and ensure that it gives you the outputs you're expecting for that sample set. Sample set being something that mimics reality, but the idea being that you don't need to test every part of your software system at the same time in order to test the functionality of some individual part. This also makes it a lot easier to refactor, to replace, let's say you wanted to write a new filtering module or a new vision module. If you had a very mammoth unitary architecture, you could have to rewrite a lot of your code because all of it was very, very dependent. But if things are segmented, split up into functional units, you can simply replace whatever functional unit you're interested in, be that a vision system, be it a vision module, be it a function that computes the average of two numbers, whatever. The point being that you can design and replace individually, because rather than being composed of one program, your system is composed of a set of related pieces, each of which has a defined functionality. So replacing a piece with a piece of equivalent, although presumably better if you're refactoring functionality, will work. This also allows you, generally speaking, to abstract away repetitive functionality. So anything that your code needs to do multiple times. I mean, for example, when you want to tell your sub to go forward, it probably has to, at some level, that has to translate into a large number of low-level commands to send a signal to the motor controller to run the motor, send a signal to the motor controller to stop the motor, probably a lot of signals because you need to run multiple motors to do that. Then you have to start the timer for however long you want to run. That's very complicated. But if you describe that in a way at a high level, so it's just a function, if you will, so it's one defined procedure that encapsulates all that information, because you're probably going to want to spend a fair amount of your time going forward, then that means that, for one, you only have to test it once, because either your go forward function, if you will, works or it doesn't. It should work anywhere you use it. And two, if you end up needing to change it, if you decide that you want to go backwards instead of forwards whenever you went forwards for whatever reason, you can. It's probably an unlikely use case, but oftentimes that kind of general functionality does need to be changed in minor ways, and it's very useful to be able to do so easily without just searching through your file and figuring out all the instances where you did something like that, rather abstracted away. Part two. So the other factors that go into choosing a good design for a software system. Number one, language choice. You want to choose a programming language, intelligently, with knowledge of the context of whatever software requirements might be pertinent, i.e. whatever you care about the context of what you're trying to build a system in. If you want to write a high-level logic system, you probably don't want to be writing it in assembly. Likewise, if you want to write a very fast array math, you don't want to write it in Haskell. This is fairly simple stuff, but it is important. And more so, I think, are what are sometimes technically referred to as domain-specific languages, but simply the idea of creating, whether it's a language per se or simply a suite of functionality encapsulated in another language, be it object-oriented programming or functional types or whatever syntax you prefer. But the idea of creating a custom abstraction layer that provides things like go forward or whatever to describe sort of the structure and logic of your programs in a way that makes sense for the context of what you're using. And again, this is a little vague. I'll get into some more examples in a second. But all this means is simply making the functionality of whatever you're writing engineerable with whatever level of abstraction makes sense. If you're writing a mission system, you don't want to deal with the low level of how to run the motors. You just want to deal with what to do based on this set of stimuli, based on where this object is. I want the sub to do this, to go to this place, to run this action, run this actuator. And you want the parts of your code base to deal with how the sub does that, say how it translates velocity desires into motor values, or how it translates vision inputs into object coordinates to be elsewhere, so that when you're working in mission, for example, you can focus on the logic of mission, so that when you're working in vision, you don't need to worry about the logic of mission. You can just focus on translating a set of pixels from your camera into a set of object coordinates for whatever other parts of your system want to use it. Along with that comes adaptability versus efficiency. And most obviously, if you're using a Turing-complete language at some point, it's anything is doable, but you want to choose a language well such that it makes sense for your use case, as was mentioned earlier. And finally, I'm going to go over at the end a few general coding practices things, which can be overhead is to be avoided at a general basis, but there are cases in which it's useful, and I think it's worth at least knowing. All right, so to dive deeper into segmentation, as was covered briefly earlier, you want to have all of your code base encapsulated in distinct modules or functions of functionality, which take in some input, if you want to describe it in data sort of sense, and produce some output. Generally speaking, no function should do multiple things at a high level. I mean, obviously, a mission that navigates around the wire does multiple things. It goes forward, then it turns, and then maybe it repeats that in a loop. But at the level of abstraction which you're looking at it, that simply goes around a wire. You can describe the functionality of that piece of code in one line, although one line is an arbitrary metric, but it has a singular goal that it has a start point where your sub is in front of the wire, or I guess the wire is some vernacular terminology. I just mean the pipe thing that you get points for circumnavigating around or going through, depending on which you choose. But anyway, you define a function in mission, for example, that will, given a start state in front of the wire, navigate the submarine around the wire, and that function is defined and testable by its ability to complete that task. It doesn't need to do anything else. You don't need to write in anything else. And if you want to do something else, you can write a different function. If you want to have one function to circumnavigate the wire and one function to just pass through, depending on time constraints or whatever, that's fine, and you can encapsulate those perhaps in different functions, combination of other functions. Maybe you have a function that turns or a function that goes straight. And obviously, those can be shared amongst the two different implementations of wire navigation. But the two different implementations of wire navigation, they do different things, are separate functions. Again, this is a generalization, but the idea is that you want each thing that your sub does at whatever abstraction level you care about is unitary, then you can just combine them in whatever way you want without ever running into repetitive code. If you need to circumnavigate around the wire 5 times, you don't need to write a new function that circumnavigates around the wire 5 times. You simply call your circumnavigate wire function 5 times, which is a far more general and far easier way to do things, because with that methodology, you can do anything any number of times, and you can combine things in sort of hierarchical structure. Maybe your whole mission is simply a sequence of task functions, one that hits a buoy, and the next one drives to the wire, and the next one circumnavigates the wire, etc. And to this end, you want to identify at a high level, as you begin to split these up, what parts of your system are distinct and can be easily separated in this manner. Clearly, at least as CUAUV uses it, you have generally your mission system, which is what translates information about the world, usually in a filtered format. So where some object is, what tasks I've done already, how many points the tasks are worth, what's the state of the submarine, etc. What do I know my capabilities are? Translates that into action, into what you want the submarine to do. And you have vision system, for example, which takes whatever input your cameras give you, pixels on a screen, and translates that usually into object coordinates, because your vision system probably cares about what objects are where at any given time. You have maybe your acoustic system or hydrophone system, which tells you where the pinger is relative to submarine. You might have filtering systems, which are intermediary on data, so you'll pass into a filtering system some data, maybe from your inertial sensors like accelerometers, maybe from vision. Your filtering system can output a filtered version using whatever filtering algorithms you want, but the point being is that it operates on data and produces data. It doesn't read from any sensors directly. You might have electrical interfacing, such as systems that interface with any electrical stuff on your submarine. Maybe that's thrusters, actuators, some of that could be involved with sensors. And again, you want that to be separate from, you want the code that allows your computer or whatever you're using as the brain of the submarine to talk to the camera to be separate from the code that actually translates the camera information, the pixels, into object information, because then you can replace one without replacing the other. We can replace a camera on our submarine without changing any of our vision code, because our vision code doesn't really depend on camera intrinsics. It simply depends on getting this set of pixels that represents this, relative state of the submarine. The camera points in a certain direction, for example. And maybe you have some self-monitoring parts which look over how your other systems are working and restart them if need be. So to look at, I will often use the UAV as a case study since I happen to be on it, and so can perhaps talk about it most effectively. But our system is split up much in this way. We have a distinct mission system which focuses on high-level control code. So what to do and when, and to some extent how to do it, although how at a very high level, how to navigate around the buoy in the sense of what sequence of move tasks, move functions, if you will, to execute in order to circumnavigate around the buoy, not how and how to run the motors. How to run the motors is the job of the controller. And we have a vision system, which, again, as mentioned earlier, translates vision information, translates pixels on a camera into object information. So where is some object? If I'm looking for the torpedo target, I want to know mission where that object is relative to the submarine. The vision system's job is to translate what it sees, pixels on a screen with some colors and some location and structure, into that object information that can then be acted on by other systems in the submarine. Our vision system is also split up itself into modules, so you can switch on and off recognizers for different elements. Obviously, you're probably not interested in looking for the submarine target if you're at the other end of the pool, so there's no reason to run that, both for performance reasons and to make sure you don't get any misidentifications. Now, in some cases, it can be beneficial in case the sub isn't where you think it is to have some of your other vision modules on. It's a trade-off, but the idea being that we can essentially decide what we want to be looking for and use that to inform what we tell our vision system to look for based on where we know we are. And then we have the unified serial daemon, which is, as mentioned earlier, sort of the electrical interfacing part of our software stack, which just abstracts away variant of RS-232 to talk to all our sensors and thrusters. And that essentially abstracts that away into a specific set of functionality, and translates whatever high-level commands we use in the rest of our code to actual calls to the electrical system. We have a Kalman filter, which transforms sensor data mostly, in particular inertial measurement data, how fast we think we're going, what we think our orientation is, and filters that down to provide a more accurate estimate of substate. And we have our controller, which transforms locational desire. So we tell the controller that we want to go at a meter a second forward, or we tell the controller that we want to hold pitch at 70 degrees, etc. And it transforms those into thruster values. So what to actually tell the thrusters, which in our case is just a speed from negative 255 to 255 or something, what to actually tell the thrusters to do. All of these systems are, for the most part, separate pieces. They're individually constructible, so someone can just build a new vision system, and as long as it interfaces in the same way with the rest of our software suite, it will work without issues. Likewise for USD controller Kalman vision. They're individually, again, for the most part, debuggable, although you do run into some issues related to how systems work with each other. That's unavoidable, but you just want to minimize it. So for the most part, we can look at our vision system and say, is the vision system identifying this object correctly, and we're not worried about whether or not mission is doing what it should with the object data once it gets it. We're just worried about whether the vision system provides the correct data in the first place. Likewise, we can debug the controller by setting a pitch of whatever or roll of whatever and seeing whether the controller actually responds correctly to that input value. We don't care about whether that input value is being set to what it should be set in some other part of the code. We just care that the controller performs its job correctly. Usually this resolves in an interface of sorts, as you've all seen in your design courses. Although it's often informal, often decided simply by necessity and time, and whoever happened to be working on the projects at the same time, you don't necessarily need formal interfaces, but you do want a unified way to communicate with whatever piece of software you're communicating with when you do segment things into pieces like this. So in our case, this is mostly done by something called shared memory, which is a system that we use. It's technically a POSIX compliant block of RAM, which is some fancy terminology, but it just means that RAM on the computer, so literally some memory that has proper read and write locks, such that you can have multiple programs reading and writing to it, quote unquote, at the same time without issue, although really at the same time, but you can treat it like it is. And this allows us to easily have different parts of our code interface with each other without needing to know what they will be interfacing with. You don't have to send messages per se. Vision can just take in data as we run a lot of our stuff as daemons, so they're all running simultaneously at the same time. Vision can simply take in data from the cameras or what have you and output it to object coordinates in shared memory, and then anything that wants to can read it. It can be mission system, it can be some debugging tool, it could be something else, whatever. Vision doesn't care. Vision just writes the information to that location, and then it's globally readable. But I mean, essentially, it's a global state, but it's just very easy to use. And likewise for the Kalman filter or whatever, anything can just, the Kalman filter is great, so the Kalman filter doesn't actually interface with anything directly. It interfaces with shim. It reads data from our sensors, which put in shim. It writes other data, which is filtered sensors to shim. People often sort of define a hierarchy of languages, usually in terms of what's called low level versus high level. You have assembly at a very low level, so very specific definitions of how you want to do things, low level assembly instructions, jumps, etc. Then you go on C, C++, and Java, and nightmares, Java, Python, and then maybe if you want to get really high level and crazy, OCaml, Haskell, sort of functional languages. Those are sort of general purpose, sometimes what are referred to as scripting languages. And then you have, as some teams use, robotics directed custom languages. For example, these are similar in some ways to Lego Mindstorms, which you might have used. A lot of people use ROS, Robot Operating System. At some level here, the trade-off is simply flexibility versus ease of use, or ease of use initially, as I'll get into in a minute. With scripting language such as, for example, Python, you have a lot of flexibility, a lot of control of what the language allows you to do, but it doesn't provide built-in interfaces to whatever systems your sub might be using. But I think, at least in our experience, the better solution has been to use a flexible language, but build custom abstraction layers. So CUAUV uses C and C++ for vision, although that could just as easily be in Python, because we use OpenCV, and OpenCV has C bindings in Python, so you can write Python code that actually just calls C code, but you can put some of your logic in Python, and it's you care about is having the stuff that needs to perform in low-level language, i.e. C, C++. We also have the unified serial name, it's also in C for interfacing reasons. And then for most of our other stuff is in Python, the mission system, which does a lot of high-level logic and uses some high-level classes, abstract constructs. The Kalman filter and the controller are both in Python, although again, both of them use NumPy, which is just a set of bindings to very fast optimized C or in some cases Fortran libraries. So in a way, we're putting the logic of our code in a high-level language, but the computational part of our code in a low-level language, which is the optimal way to do it, you know, as best you can. And that allows you to, I mean, when you're writing a high-level thing, a Kalman filter, a mission system, a controller, you don't want to deal with some of the nastiness that you have to deal with in low-level languages, memory management, you know, pointers, etc. You can focus on, you know, code logic, how your code is supposed to work, how you're processing, how you're filtering the information, how you're deciding in a mission system what to do, as opposed to low-level syntax or implementational particulars, you could say. You don't want to focus on whether or not your program will segfault because you forgot to deal with an L pointer. When you're writing a high-level mission system, you want to focus on whether your mission performs logic correctly, whether it decides based on a set of input constraints what to do correctly. And we try to accomplish this by using something which I guess informally I'll term a quasi-domain specific language, which is simply a way to give one the flexibility of the scripting language. We write our code in the scripting language, but still have the efficiency, still have the abstraction layer that something like ROS provides. And really, this is what ROS is. ROS is just an abstraction layer over another language. You know, your computer doesn't execute ROS code per se. It just turns that into something else which it can execute. And rather than use ROS, I think it's oftentimes a better idea to define your own abstraction layer, to figure out what exactly you need, how to translate your high-level commands to go forward or run motor into low-level functionality, then write your own custom abstraction layers, which can be, as mentioned earlier, segmented from your system, such that they can be treated as in other parts of your system as equivalent to something like ROS, something very high level, but you can define the exact low-level operations that they need to carry out. And in doing so, you have complete control over your stack, and you understand everything that actually goes, everything that takes place from how you translate the high-level code into low-level action. And of course, this isn't a, libraries are very useful and should be used in many cases. We use a lot of OpenCV for our vision code. We use NumPy almost exclusively for anything computational. But just understanding what things it makes sense to customize to your use case is usually very helpful, and any abstraction layer that you build yourself, you will probably understand much better than anything you use that someone else just built for you. How to do this? So there's many ways. You can have, essentially, you want to be able to have the ability to create custom data types. You want to say, you want to create a construct that is a task or a function that abstracts away a level of functionality. So you can say run forward as a data type, and you can manipulate it as a data type. You can repeat it. You can transform it, and whatever transformations apply to run forward, if we want to call it something like a task. There are many ways to do that implementation-wise. You can do it with functions in the functional language proper, or in Python, where functions are really objects, although, again, the differentiation between functions and objects isn't particularly meaningful in this case. You can implement this with either Python, C++, Java, if you will, although I recommend against it, etc. CUAUV uses this, I guess, most immediately for our mission system, which creates, in a sense, a custom data type, a task, which defines a set of functionality, how to run a task, what to do to initialize that task, to stop that task, ways of analyzing a task at an abstract level, whether a task is done, what its status is, etc. And that allows us to write other functions on tasks. So say a function that combines two tasks based on some conditional property. If something is true, we want to run task A, otherwise we want to run task B. This means that you can abstract away your control flow functionality at a level that makes sense. So we can say that if I can define another task which simply chooses whether or not to run one of two tasks based on a conditional, then combine that task just as I would any other task, because we have essentially a set of functions from this new data type that we've created, tasks to tasks or to other things. that can be defined abstractly so that combination can be achieved without just writing a lot more code, rather than using what you already have and enabling combinations of your custom data types rather than just defining a lot of new data types. As you can see there in a code example, so I can create a forward task and a turn task, and then if I want to run both, I just combine them with a combinator called concurrent, which just runs two tasks at the same time. And it doesn't care what the tasks are, it simply cares that they're tasks because it knows how to deal with tasks. I mean, this is fundamentally just a method of abstraction, but it's a method that makes sense in our particular use case and makes it much easier to do something like run tasks or define a mission system, which can run a lot of tasks. It also makes execution flow very clear. When you read concurrent forward task and turn task, you know exactly what the sub is doing. The sub is going forward and it's turning at the same time. Whereas if you had to specify that at the lower level or specify, somehow intersperse this code from forward task and turn task, it would be far less clear what was actually going on. This becomes more of an issue, especially when you deal with more complicated combinations of tasks, something more complicated than simply concurrent. Let's say you have some tree of tasks which have to be run in a certain order. It's very hard to deal with that unless you have a way to abstract that away to a data structure that defines, for example, execution order as concurrent does. Now, finally, for perhaps the least entertaining part of this presentation, but coding practices. We do a few things in particular on CUAUV. We use, to some extent, code reviews, which are a time sink, but can be useful to avoid two types of errors: trivial errors, so by having someone else look at your code, especially if it was written at an odd time in the morning, as our code often is, and catch any trivial errors you might have made, but also to catch logical errors. If you're designing a very high-level piece of software, you want to ensure that the logic of your software functions correctly, that it does what it's supposed to. And having someone evaluate that can be very useful. Mostly we use this for particularly critical pieces or sections of code, parts of code where it's integral that the code function exactly as specified. We don't want our mission to make the wrong decision, so we have multiple people look at it. Likewise, if we have a piece of code that's determined that kills the mission because the time has run out, we want to make sure that it doesn't accidentally kill the mission because it forgot to divide time, which was in milliseconds by 1,000 or something stupid like that. But you just want to make sure that anything that could cause critical damage to your sub's functionality or functionality on a software level is evaluated simply by multiple people. Of course, version control is a must. I'm sure all of you use this. We use Git and recommend it. There are other options. SVN doesn't work as well for code. The diff control isn't as good. The multi-user access at the same time isn't as good. Merging is kind of a mess. Darks, which is its own thing. I have not used Darks extensively, although I think that's an alternative to Git if you're interested. Version control enables easy tracking, rollback, backups, etc. It enables multiple people to work on a code base very simply, and we'll be able to submit changes to the same systems and even in some cases the same file, and it's all dealt with automatically, generally intelligently. We host, mostly for historical reasons, a custom Git repository on a local server, but GitHub or Bitbucket will also do its job just fine. So in summary, software design is simply the process of designing a system such that good programming is enabled. You want your programmers to only have to write a particular piece of functionality, a particular function that does something that transforms some data input into data output once. You want all the components that are critical to the functionality of your system to be isolated and easy to debug, to figure out what they do and how to fix them if they go wrong. You want to separate as best you can your logic, your declaration, what happens, from your implementation procedure, how it's done. This is done mostly through abstraction layers. So as was mentioned earlier, for the task example, you just state that you're running two tasks at the same time. And then somewhere else in your code, it is specified how to actually run two tasks at the same time. This allows updates to be made easily with little fear of process effects. You don't want to have to, when you update your code, worry about all the other dependencies that it might cause problems with. You simply want to be able to ensure that it fits the interface or the set of functionality for which it's supposed to be providing, and if it does, then it should just work. You want all your software members to be access the systems, but you don't want them to have to know. You want them to just have to look at the interfaces, look at the what of what other systems do, and use that to construct their own particular how their system does what it's supposed to do. You want to choose languages appropriately for the context and the task in question, and use custom sub-languages or abstraction layers, whatever terminology you prefer, in subsystems where they're useful. And to put it even more succinctly, coding is simply abstraction. At some level, all your submarine does is process a stream of zeros and ones into another stream of zeros and ones. But abstraction is what enables power in this. Abstraction is what enables you to transform that stream of zeros and ones into something that makes sense from a programmatic level, from an intuitive level, whatever, and embed in that intelligent logic that allows you to tell yourself what to do. Done improperly, a software system can hinder functionality. It means that you have to worry about a lot of cross dependencies. All your code is dependent on each other, etc. But done well, it allows all your programmers to focus entirely on whatever specific goal they're working on or they're caring about, and abstracts away everything else into layers that just make sense from a declarative level. Alrighty, questions. You're welcome to submit questions via email. I'll be watching again, as mentioned earlier. My email is cwg46@cornell.edu. I will also take questions in group chat at the webinar. And I'll sit here for as long as questions come in. So it looks like we have a question here from SRMAUV. We do not currently have sway PID controller for doing closed loop velocity distance control. What would be the best approach to align with the buoy target with sway movement using vision input coming at a relatively slow rate? So the best approach is probably just to write a PID controller. If you're talking about, when you say we do not currently have, if you're talking about a hardware PID controller, you can often write a software PID controller. That's actually what we do. We don't have hardware PID per se. We just use software PID in our code base to perform a PID on our thrusters at the velocity level. If you can't do that, you could also look at, if you're trying to align with slow input, essentially run PID on the input instead of on your motor. So look at the rate of change of the input, perhaps the acceleration of the input, and try to predict what will be next, so you can better target your motors for alignment. That's generally what I'd recommend. And even if you don't have a full PID controller, you can build something simpler. In some cases, a simple PD controller will do most things. You don't always need I, depending on what your actual roadblocks are there. Alrighty, well, that's the end of questions, and I think we'll go ahead and be done for the day. Again, sorry for the technical difficulties earlier. I will put this PowerPoint or Google Drive presentation, as it were, up on our site for everyone to look at later. If you have any questions, feel free to send them. Again, my email is cwg46@cornell.edu. And thanks for coming. Best of luck at RoboSat.